Hello everyone, welcome to week 9 of Digital Media E10, Exposing Digital Photography. This is Digital Cameras Continued. Now, as we've grown accustomed, just a few reminders. Problem set 4 is due tonight. Project 4 is due a week from now. This is the last of the numbered projects before we transition into the final project. And we are quickly approaching the tail end of our really hectic 1 week after another project and problem set release schedule, which has been equally hectic, I know, for the TAs of this class who've been working really hard to get grades and feedback to you back within a reasonable fashion. We are aiming for just over a week after your submission to us, and so we're still trying to maintain that schedule, but realize that we're doing our best, and there are a lot for us to grade, so I hope you will bear with us as we try to provide that feedback. Problem set 5, the last of the numbered problem sets, is released today, or it will be released a little bit after lecture. And this one is a little bit different from the other problem sets. So the other problem sets have just really been, a bunch of questions, and you sit there and you answer them, and they're all pretty independent of each other. Perhaps the histogram one had sort of a continuation in another question, but this is an appropriate time to realize the problem set 5 deviates from those because there are 2 versions of the problem set. There's a version for undergraduates. If you're registered for the class as an undergraduate, then you will do one version. If you're registered for the class as a graduate student, on the other hand, you will do the other version. Now, as an undergraduate, I just want to make clear, you can actually do either of the 2. And if you're a graduate, you can do both if you want, but what we are going to grade is only the version that you submit to us. And there's no extra credit involved if you do 2 or anything like that. So what separates this problem set from the others is that the graduate version of this is a lot different from the ones that we've seen in the past. And in particular, we're going to be looking in depth at a specific digital camera, one that exists in a probe that is as far away from Earth as pretty much any man-made object is at this point, with only a couple of exceptions. But it is specifically, we're going to be looking at the imager in the New Horizons probe, which has been responsible for a lot of the fantastic images that we've seen from Pluto and its system. And specifically, what we're going to look at is not just a collection of pages that or resources that show us, that summarize some of this information, but instead, we're going to be looking at the raw scientific paper that came out of the people that developed this imager. And we're going to be taking a look at that and trying to mix some of the things that you've learned in class and trying to figure out some properties of this imaging system. So this is, it's all going to be one cohesive problem set for those of you that do the graduate version of it, where we will analyze some basic things of the imaging system in that. And specifically, there are more than one imaging system on this probe. We're going to look at one specifically, but you'll be asked also to just take a look and do some small research into the other one and find out how the 2 imaging systems are different and what that actually means there. So I'm actually really excited about this because I was reading this paper earlier today, and really for the most part, for our purposes, you can skip over a lot of it. There's only small chunks of it that are really extremely relevant to it. And don't worry about copying down the URL or anything, or even the title. We will provide a link to that in the problem set itself. But I was really geeking out over this because there's so many really interesting things that separate this digital sensor, this digital camera, in this device that has to be flung out of the solar system at high speeds compared to what we have on Earth, that it's useful to take what we know and see how we can pick apart that imaging system and determine what similarities it actually has to the systems that we have talked about in class and that we've grown accustomed to actually using, and what is actually different from them. So some of the engineering that had to go into ensuring that it would be able to work in extremely cold temperatures, for example, is just a really fascinating thing, and a lot of other things that make this kind of unique. So I'm excited for this problem set, and hopefully you are too. In next week, not today and not on Saturday's section, but in a week from now, I'll provide some resources as well to the section leaders so that they will be able to look at a similar paper in an imaging system, not in the New Horizons one, but instead look at tackling some of the same questions that we proposed in the problem set for a different spacecraft imaging system, the Rosetta spacecraft, which is orbiting a comet. You may remember from last year, we actually landed on a comet, which is actually pretty cool. There were some mishaps, but still all of the imaging systems were functional, and we were able to get some fantastic images from that as well. And so we'll look at that in a little bit more depth in sections, so that we can sort of get a taste for what problem set 5 will actually look like. But it's really kind of fascinating because I mean, just reading this and how this sensor works is so different in some ways from the sensors that we have on Earth that it's really fantastic to see how those things actually function. Now, towards the end of being able to get to that point, of being able to answer the questions in problem set 5, we have a few more things to talk about. Oh, and the reason that we have a cat up here, I'm told that apparently today is National Cat Day, and I didn't actually confirm that that's the case, and I realize now that anyone could actually tell me that it's any day, and I will end up putting a picture of it up on the slide. So I'm going to start checking these, but apparently today is National Cat Day, and so here's Newspaper Cat, because this is how you should feel when you're reading the project, very sophisticated and informed. Okay, anyway, so we've been going over last week some properties of digital cameras, and these will be helpful not only to understand a little bit more about how your own digital camera works, but also how to answer the question specifically in problem set 5 as well. So we talked a bit about the different sizes of sensors that can exist in digital cameras and how this can impact image quality, specifically the field of view that can be present given a lens and the digital system that we are using. And if we are using a smaller sensor for the same lens, then we're essentially cropping out that center portion of the image. Essentially then, if we have the same resolution, we are somewhat zooming in on that center portion of that image. And how, as a result, I pushed a button on accident. I think it was this. Let's see, we might have to do an emergency pause session. Please hold. Thanks. Okay, it's 3. Good to know. Thanks, Jordan. Okay, so before we were talking about a crop factor and how this actually translates to a different field of view depending on the sensor that we are actually looking at. And we use this as a way to compare the field of view of lenses on different sized sensors and how we can use this multiplication factor to determine how much our field of view changes for a given focal length from one sensor to the next. And from there, we talked a little bit about how this actually changes with regard to this idea of talking about the depth of field within a sensor, and how it appears as though smaller cameras have inherently a larger depth of field, but taking all the elements into account, we actually realize that our larger digital cameras with bigger sensors actually have that same capability. We just have to change the settings in order to accommodate those differences in the way that the sensors are sized. Now, before and after that, we actually talked a little bit about dynamic range as well, about how this is essentially the difference between the full well size, the full capability of our pixel, divided by whatever the lowest possible amount of signal that we could actually determine in our pixel. And so we actually were finally able to say for the first time a little bit more concretely about why ISO is not really changing the sensitivity of the sensor at all, but instead all that we are doing is using the same level of detection that we were using before and just changing some multiplication factor to try to make that the signal that we did receive bigger or smaller, as the case may be. So as we talked about, when we increase the ISO, we're not changing the sensitivity per se, but instead what we are doing is maintaining the same sensitivity, but just taking those values and multiplying them by some factor to try to make them appear to be brighter, which is maybe a fair way to do this, except that this might mean that we are then impacting our dynamic range if we are saying that our full pixel is then half or a quarter or an eighth the size that it was initially. But again, there's some electronic tricks that happen in a sensor that allow us to lower the amount of noise in the lowest possible number of photons that we capture and therefore not have quite so bad of a loss in dynamic range. Then just to quickly tie up some other things as a review from last time, we talked about how there's multiple types of sensors. There's active pixel sensors and passive pixel sensors, and there's a difference between the two. And what we will find is that passive pixel sensors are, especially CCDs, are more prevalent, even though they happen to be a little bit more expensive and they use a little bit more energy, but at the same time, they generally have better noise characteristics than their CMOS brothers. Then a couple of other things. We talked about sensor size, or really how pixel size can dictate to a large degree how our dynamic range might actually be impacted, where larger pixels might be able to capture more pixels. And as a result, we would then be able to have, or rather, our larger pixel size will allow us to capture more photons, and as a result, have a higher dynamic range. Then we scared everyone by showing you this circuitry diagram, but really the main takeaway from this was not in how it functions underneath the hood so much as that there's just a lot of stuff going on at every single pixel, which really occludes perhaps all of the elements of the circuit that actually capture the light and do something with it, and how the micro lens then is an important element in our setup of a sensor, because it allows the light to be focused onto the specific photodiode at an individual pixel site. Now, at the very end of last week, we started talking about this kind of outlandish notion that the digital sensor itself may not actually be capable of capturing color, and instead we have to have some other mechanism to provide color information to the camera. And this is, in fact, still true, and we saw a little bit about this in the video that we showed at the end of last week, but at every single pixel location, our photodiode really can only capture grayscale. It can only capture the intensity of light and not, in fact, the wavelength of that light. But it's also important to realize something else as well, which is that this photodiode might actually be receptive to only certain wavelengths. So in other words, they may make it so that it is able to measure the intensity of visible wavelengths, but perhaps not of infrared wavelengths or ultraviolets or some spectrum that we actually are not able to see. And this is an important thing. We want to only measure electromagnetic radiation or light in the visible spectrum, because if we are capturing and recording these other wavelengths, then we will get some strange aberrations in our images when we see some waves that we don't actually see visibly. And this is actually important because a lot of the photodiodes that we have in digital cameras are sensitive to visible light, but they are also sensitive in infrared. And so we will typically have some optical filter in our sensor that essentially blocks infrared light so that our photodiodes are only capturing visible light. There's some modifications that people make where they remove this optical sensor or this optical filter to allow infrared light to be captured by the sensor, or they might even install the opposite, where it blocks visible light and only allows infrared light to pass through, thereby allowing you to capture fully infrared images, which have a very unique look. What you get to see is essentially a different way of looking at the world, but it is still somewhat grayscale because, again, it is just measuring the intensity of those wavelengths, not necessarily the color. You would have to apply some sort of false color to that information in order to view it. Okay, so we have pixels here. This is one pixel, sort of looking at it from the side, and there's a variety of layers that are involved in the creation of this pixel. We have up top the micro lens. We have immediately below that a color filter array, which we'll talk about a little bit more in just a second. And then below that, we have a bunch of electronics. This constitutes all of the circuitry involved in the pixel, which we just saw in the prior slide, including all of the transistors and everything that's required to actually read the data from this pixel and capture the information provided to us in photons. And we can see that it really creates this sort of well. There is only a small portion of this pixel that allows us to capture the information, which is why we need to have a micro lens to focus as much light as possible that's falling on that pixel onto a very small area that actually registers that light. And I mentioned last week, but I want to reiterate that a lot of improvements can be made in the performance of digital cameras, not just by increasing the circuitry, or not just by improving the circuitry or improving the performance of the photodiode, but also making improvements in the micro lens as well. If it can focus the light onto a photodiode more efficiently, or if it can reflect less light or scatter less light to areas that are not on the photodiode, then we will improve the performance and get much better low light capability out of that sensor. And in fact, a lot of the improvements that we've seen in the past, around 10 or 15 years of digital cameras, have been in the creation of improved micro lenses. So let's come back to this idea that we were talking about a moment ago of the notion that an individual pixel can't actually register color. And we sort of alluded to a possible solution last week, and we saw it in the video as well, and that is that we might be able to use a filter to try to determine which of a specific color is being registered at an individual pixel. So if we look at the color filter specifically on this pixel, we see that it's, in this case, red, and so we are only allowing red wavelengths through, which means that at this pixel, the photodiode will only be registering red wavelengths, or the intensity of red color in your image. And as we have grown accustomed in dealing with digital photographs, we actually can have a variety of color filters in a specific array, in specific arrangements, that allow us to then reconstruct the image. The reason that I say that we grow accustomed to it is because the most common ones that you might see are actually the colors that you would also expect as a result of all of the things that we've talked about. We might have a red filter, a green filter, and a blue filter, and in combination would we then be able to reconstitute the original pixel, all of the color of the pixel at a specific location. But there's an interesting problem here, which is that these color filter arrays don't, or these color filters don't actually change on a per pixel level. We have every pixel tends to be assigned a single color filter. And the most common pattern that we see that results out of this, because we have 3 filters here and we need to arrange them in sort of a square arrangement in some repeating pattern that would allow us to reconstruct the original image, we typically see this pattern, which is called specifically the Bayer filter, or the Bayer color filter array, because it has this specific pattern. If you look at blocks of 4, you can see in the far left side, we have a blue, a green, and then a green, and then a red. Why do you think we might have this arrangement of colors? So put another way, why do we seem to have, at every block of 4, why do we have so much green? Why do we only have 1 blue and 1 red, but 2 pixels dedicated to green? Yeah?
Is it because the blue and the red are more vibrant than the green?
The blue and the red are more vibrant than the green. It's almost the opposite based on our perception. So if you remember from our discussion of luminance back in the histogram lecture, we were talking about how our perception of brightness comes primarily from the green wavelengths. And therefore, of these 3 colors, what's more important for the camera to be able to reconstitute is the green one compared to the blue and the red. It's much more important for us to have a much better idea of the green wavelengths to more accurately reproduce the image as we would see it compared to what perhaps it actually is. Did I see a question here?
Is it just because it's used for like highlights if you're talking luminosity?
Is it only because what? I'm sorry?
If you're using it for reconstituting like highlights, is it?
So it's not just in highlights. It is because of the relative importance of green, because when we perceive, if you recall from when we were talking about luminance and the importance of the various wavelengths, because of the ways that our cones respond to different wavelengths, we have the ability to distinguish many more hues of green than we do red or even blue. Therefore, being able to reconstitute colors with the most amount of green information as possible will ensure that we are then able to reproduce this in a natural way. So this color filter array repeats over the entire sensor. But this kind of implies something important, which is that at a single pixel, we will only have various gradations of a specific color, either blue or green or red. We don't actually then have the capability to look at the entire spectrum of colors at a single pixel. But this may kind of be, this might go against your own experience working with digital images. When you zoom into 100% or even further on your digital images, you may realize that individual pixels do seem to be made up of full amounts of color information. It doesn't seem to be the case that there's one pixel of some level of green from black to green, and then right next to it there's another pixel that's some gradation of blue and red and so on. So there must be some way that we can then try to figure out at every single pixel location what those colors were that originally constituted that image. And we'll get to that in just a second, but I do want to mention something. This is the most popular type of color filter array that exists, which is the Bayer color filter array, and it has this pattern, sort of blue, green, green, red, if you look at it, a block of 4. But notice that if you look at any four blocks arranged in a square, you get precisely that same information. You have 2 pixels of green, a red pixel, and a blue pixel. It doesn't matter where you're looking. You can find any 4 blocks that actually has that, so long as they are arranged in a square and continuous. And that is important. But there are other types of color filter arrays as well. There are some manufacturers love to just kind of go out there and create all sorts of crazy color filter arrays. I think Sony in particular did a lot of marketing a few years ago, or several years in the past, where they have created some color filters. Oh my God, sorry, keep pushing that button. Where they created some filters that had like emerald in it and cyan and I don't know, so it's just a bunch of colors and yellow, and they said that this improved color fidelity and a bunch of other marketing speak, but I don't think that necessarily we see an improvement in our resolution or in the capability, the color capability of our cameras when we have other color filter arrays, especially because companies have grown so accustomed to using this one specific color filter array that they have become very good at tweaking cameras and the algorithms inside of cameras to recombine all of these individual colors into their original components. So let's put this into a little bit more concrete of a discussion. If we have a color filter array that looks like this, which is essentially the same thing, but it's just offset a little bit, we have here a sensor that on the far left is made up of a total of 16 pixels. And we have at each pixel location a color filter applied to every single one of these pixels, and it is arranged in this Bayer color filter array pattern, this Bayer pattern that we have seen. If we want to try to figure out what color exists at every single pixel, we might be able to do it, but it's a little bit of a fudge. We can't actually figure out at each individual pixel location what the color might be, but you can imagine that if you knew the red component, the green component, and the blue component, you would be able to figure out what color perhaps existed between those pixels. And so that's what we can do, is that we can reconstitute the image that existed in this block of 4. We have a blue, a red, and a green pixel, and so between that we might be able to say, okay, well I know approximately what the color value should be among those 4 pixels. We might be able to do the same in this quadrant on the far bottom left, and the same for the upper left, and the same for the top right. Because we know the value of green and red and blue across those 4 pixels in this quadrant, we are then able to basically just combine them and say the color here should be this value. But the great thing about this array is that we can shift over by one pixel and still have the same capability. So at the very beginning of this example, we were looking at this bottom right quadrant where we had a red pixel, a blue pixel, and 2 green pixels, and then we were able to recombine that into the original color. And we were able to do that, the same thing for this quadrant, but notice that we're also able to do the same for these 4 pixels between those two. So essentially then what we are able to do is to recombine these individual color channels into a fair number of pixels, but it's not going to be the same number of pixels as I have pixel sites on my camera. So in other words, we can break it into quadrants, just like we're seeing here in the middle, and we can create at this, sort of this middle dot in each quadrant, we can recombine those and figure out what the approximate color should be across all 4 of those pixels. But then we can do the same thing between each of these quadrants as well. And so what we get out of this sensor that has 16 pixels are 9 pixels that have full color information. So you can see here numbered in this far right grid all of the original pixels that we can then pull out of this 16 pixel grid. Now this sounds really bad. It sounds like, oh gosh, it's almost half the resolution of this sensor is then lost essentially because we have this color filter array. But really this is only a bad thing at the edges, because it's really the edges where we lose the ability to figure out pixels. So because this edge right here only has a green and a blue, and there's no further pixels below this row that include a red and a green component, we're not able to reconstitute that, recombine it into some color that then is representative of that pixel. So these then represent an important notion in digital sensors, which is that we have an actual number of pixels in our digital camera, but the effective number of pixels that we're able to get in a digital image outside of that sensor, pulled out of that sensor by performing this algorithm, which we call demosaicing. We're taking this mosaic and we're demosaicing it into its original constituent, or its original colors. We have then effective number of pixels that is fewer than the original actual number of pixels that we have in a sensor. And this was a much bigger deal when sensors had not that many pixels along the width and the height, because, well, there were many more pixels along the edge relative to the full area, and so this issue happened. But nowadays it doesn't really seem to make that much of a difference. We're going to definitely be losing some resolution, but with the really high number of pixels that we have in sensors these days, we don't really notice this as much. If you were out at the now defunct Circuit City back about 15 years ago and you're trying to buy your first digital camera, this was something that actually made a difference when purchasing a digital camera, with the number of effective pixels that you would get out of that camera, because it wasn't the same as the actual number of pixels on that sensor. So this is kind of an interesting problem, right? Because now some of you might be sitting there kind of uncomfortable thinking, well, wait a second, I thought that I had resolution at an individual pixel on my sensor. But now you're telling me that I'm taking 4 pixels and taking the color information from all of those to try to figure out what the color would be in the middle of those. So it seems like I really have this 4-to-1 ratio of pixels to resolution. And that's somewhat true, but again, keep in mind that because we're able to look at neighboring pixels as well, if we just shift over one and be able to reconstitute pixels between those as well, that we're not really losing as much resolution as this seems to be the case. So this is great. Now we've overcome this engineering problem of having photodiodes that only register intensity of light, but not being able to register color, because now we can actually figure out what the color was at every single pixel, or just about. But are there any problems that can result from this? Can you imagine an image that if I projected this image onto this sensor, I would not be able to recreate? let me ask this a different way. Let's think about the sort of the simplest cases where I have an image that is all white, for example. I've overexposed my image, and I'm exposing all of these pixels to white color. Essentially what that means is that this pixel in the far lower right is getting all blue. It's getting a full register of blue pixels, and our camera knows that that is a blue pixel. This green one is getting all green. This is getting all green. This is getting all red. And so when I recombine those, I have 100% value for red, for green, and for blue. I recombine all of those. Now it appears to be white, just as we might expect. Now what happens if I shine just a green light on my sensor? How will that actually appear? Well, again, there's not going to be any blue here. That's going to be filtered out by that filter, so no light will hit that blue pixel. We'll have all light in this green pixel, all light in this other green pixel, no light in this red pixel, so we'll be able to recombine it into a green color. We know that we have a full complement there. And so on and so forth. These are oversimplified examples of specific colors, but the one thing that I'm not addressing here is the pattern of light. What if I have a pattern that repeats at a resolution that matches these pixels? So in other words, what happens if I have a pattern of white and then black, and then white and then black? How will this algorithm, even though we don't know the specifics of this algorithm, we can just sort of assume some general, we can just infer some general methods that this algorithm might actually use to perform the demosaicing action itself. But if I have a pattern like that, how is this sensor going to be able to replicate that same pattern? So let's think about it again. So if this was a black column on the far right, and then a white column, and then black, and then white, we're saying that we would have no value of blue and some value for green, no value for green, some value for red. It might just kind of average it out to be this weird gray color. Or in fact, it might add some preference to red because it says, okay, I see a full complement of red, and I don't know, it's kind of weird that these two green pixels don't really fully agree, but that's fine. Maybe that's just a weird pattern. So maybe this will actually be like a yellow pixel. So this is just a long-winded way of saying that we can have these so-called high-frequency patterns. High frequency being that they repeat or that they change very, very rapidly. If it matches the size of the pixel, this algorithm is going to have a very difficult time reconstituting what that original image is going to look like, or was supposed to look like. And this is, in fact, a huge problem in cameras that use a Bayer or any other color filter array, is that high, fast repeating patterns like that, like you might actually see in the pattern of cloth in a sweater, for example, or you might see on brick on the side of a building. If you get that pattern to be just the right size, if that building is just far enough away that all of a sudden it is repeating brick to mortar to brick to mortar in a very high frequency fashion, it can in fact confuse this demosaicing algorithm, and you will get output that doesn't really make a lot of sense. You'll get some strange effects that we'll actually look at a little bit later, called moira and some other really crazy looking stuff. You can actually confuse the algorithm to such a degree that it looks like there's a maze of color that runs along this pattern rather than actually creating the pattern itself. But the way to fix this problem would be to just blur the entire image. Like, what if I was able to blur it just enough that that fast pattern of black to white to black to white was blurred just enough over 2 pixels rather than repeating over 1 pixel? In that case, this would appear then to be this somewhat dull gray, but that is perhaps better than having just really unusual effects that come out of that demosaicing algorithm. And that, in fact, is exactly the mechanism or exactly the optical filter that lies atop the vast majority of the cameras that all of you own. which is that on top of all of these other layers, right here, not pictured here, but on top of all of these things, there's something else called a low-pass filter, which rests on top, and it's basically just like this sheet of glass. It's just this filter whose sole purpose in life is to remove these high frequencies or these really fine patterns that would fall across 2 pixels in your digital sensor. So among the whole list of things that we have now at an individual pixel location is, sure, we have the well, where around which the circuitry of the pixel actually exists, and in the center of the well is the photosite. And on top of that, we might have the color filter array itself, and on top of that, we have the micro lens. But on top of that, we have yet another filter, which is this low-pass filter, which is trying to fix the problems introduced by our engineering solution to introduce color into our photographs. It's not really that, it seems kind of not that great, right? You're like, oh man, this sucks. Now, not only are you telling me that I have fewer pixels than my camera actually is marketed as, is actually representing, but now it's also intentionally blurring some of these shots. And in fact, this is exactly the case, is that we've grown so accustomed to the output of an image from a Bayer or other color filter array camera that we don't really notice that they are, in fact, just not that sharp. And this is one of the reasons why a lot of hobbyist photographers and professional photographers will apply that unsharp mask, which, as you recall from our discussion in digital or in software tools, it makes the ability to find edges and increase the relative contrast at those edges to make it appear sharper. This is one of the reasons why we do that, is that those images can, in fact, be sharper than is actually represented. But there is actually another solution as well, which is just to avoid using a color filter array altogether and try to implement some camera that is then able to represent at every single pixel location the correct value of red, the correct value of green, and the correct value of blue to maximize the resolution and sharpness at every single pixel. This was alluded to a little bit in that video that we saw last week, where we could have some sort of a prism or a beam splitter that takes the incoming light, splits it into red, green, and blue components, and then we have essentially 3 sensors that are the same size, the same number of pixels, and all that. And every pixel then across the 3 sensors record separately these color channels, and then we are able to reconstitute it that way. But there's another method as well, and that is a sensor that is called the foveon sensor, which uses the absorption of wavelengths in light in silicon to spread out essentially these wavelengths and record different intensities of light depending on the wavelength, depending on how far down inside of silicon it actually goes. So if we have a sensor, we're now looking at this essentially from the side. What we are seeing is that we have a certain amount of silicon, and as light travels down through this silicon, different wavelengths are being absorbed at different depths, as depths down from the top of that silicon. Blue is the first to be absorbed, and then green, and then red. So what if, at a single pixel, I have this wafer of silicon, and I inject at different depths a photosite, or one of these photo detectors, to allow me to figure out precisely what those values of red, of green, and of blue are. And this sounds like a great idea. And in fact, if you go online and you look for examples of foveon sensors, you will frankly be shocked by how sharp they look compared to the Bayer color filter images that we see now. It seems like a win-win, right? It seems like something that we would actually want to do. But there's a couple of problems with this design as well. One of them is the fact that if I have, and perhaps this is one of the major ones, if I have a photosite at the top level, at the top layer, I'm not just detecting the blue wavelengths up there. I'm detecting the blue wavelengths, but also the red and also the green. And as we get down a little bit farther, I am detecting no longer am I detecting the blue layer, or detecting the blue wavelengths, but now I'm detecting the green wavelengths, but also the red wavelengths. So really, what we see then out of sensors like this is an improvement in resolution, because now every single pixel, every single photosite is able to capture the red channel, the green channel, and the blue channel, meaning that essentially at every pixel, this has 3 times the amount of information compared to a color filter array sensor. But at the same time, this means that I now have to do different math to try to figure out what those original wavelengths are. If I have some amount of brightness in the blue sensor and no brightness in the red sensor, then I might say, okay, seems like this pixel should be blue. But it can actually be complicated to figure out if I have some spectrum of wavelengths that are being captured by this to try to figure out precisely what the color should be. So here I'm exchanging resolution for noise in the color. In fact, this is one of the things that we see in foveon sensors, is that we have then a lot of chroma noise, a lot of noise, especially in the blue wavelengths, especially in the darker regions of the scene. The algorithms just are not quite good enough, just like the algorithms in our Bayer color filter array are just not quite good enough to reconstitute all of the resolution. These are not quite good enough to reconstitute all of the colors at a single pixel. So just like we've been talking about, everything in digital photography is a give and take. Everything is a compromise. This, though, allows us to talk a little bit about something else with foveon, which is that we don't see a lot of these cameras around. I think they release one every few years, and I think Sigma is the company that actually releases, is the exclusive manufacturer that releases foveon sensors, and they produce, some pretty good cameras, but they're not necessarily across the entire spectrum of cameras like we see in out of all of the other manufacturers. They're somewhat limited in choice, and so they have somewhat limited market in terms of adoption of this technology. Yes? What do the different sizes of the sensors represent? What do you mean? So on the right side, on the right side of this image, we're looking at like a side view of the sensor. This is just meant to be an oversimplified look at if we are looking at this wafer of silicon, which is what is being used as the sensor. We're now looking at it on the side, and we're placing sensors at various depths in this silicon, corresponding to roughly the absorption of those wavelengths as it travels through silicon. So here we can see the absorption where at the very top, the blue light and the ultraviolet light do not travel very far into the silicon. So we want to put then, if we want to detect red wavelengths, we want to put a blue sensor at almost the very top in terms of the depth of that silicon wafer. And then green is absorbed a little bit farther down, so we just want to place it somewhere in this range where we would then be able to record those green wavelengths. And the red travels the farthest, so we would then be able to place red just somewhere along here. So this is just an approximate location of where we could place those photodetectors to detect that wavelength coming in from the top. So in this view, again, this is from the side, and light is coming down from the top of the image here. Okay, but anyway, we don't see a lot of development of this particular technology, which is kind of too bad, because perhaps if there was as much development in this as there were in Bayer color filter arrays, perhaps a lot of the hurdles that we see in color noise would actually be overcome. But the other thing, and perhaps the reason why foveon didn't win out, is because it appears as though they have far fewer pixels. They're typically marketed with something along the lines of 4 megapixels or maybe 8 megapixels now, something like that, which just doesn't sound that great compared to the, frankly, dozens of megapixels that you can get out of modern sensors that have color filter arrays. But again, the important thing to realize is that even though there's fewer pixels, each one of those pixels is able to capture 3 times the amount of information because each one of these pixels has a sensor for blue, has a sensor for green, and has a sensor for red. But it's very difficult to explain this subtlety and this nuance to someone who's going to Best Buy and wants to buy a digital camera. They say, well, this camera has 4 megapixels and this one has 10, so why don't I just buy the one with 10 megapixels? It's much harder to explain why they perhaps would want to go for the smaller megapixel camera. So there's actually an example that I can show you. This is now several years old, but is representative of the difference in resolution and the different problems that we might actually see between a camera that has a foveon sensor and one that has a color filter array. So here are a variety of pictures. We have, look first at the far left. The far left is a Canon 5D, which is a full-frame camera. It has excellent image quality, and we can look at that at 100%, a crop of that at 100% on the left. Now if we look at a foveon sensor in the middle, which has, of course, fewer megapixels, we can see a couple of things about it. One is that those lines, especially compared to the 5D, are just absolutely sharp. Imagine for just a moment that we have this same pattern, this angled, colored pattern that's falling on our sensor, and we're trying to reconstitute, using this demosaicing algorithm, the pixel, the color information at every single pixel. Well, along this edge, there's going to be a little bit of a problem because we have this color falling on perhaps 2 of those 4 pixels, and we're going to compute what it is, and it's not necessarily going to provide the sharpest view of that angled amount of color. But when we have a pixel, like we do in this foveon sensor, that is able to capture all of the color information, we can then create an image that looks to have the same, or in fact, improved sharpness. So arguably then, we could take this image from this smaller megapixel camera and blow it up and receive about the same information as we did in the Canon 5D. And in fact, that's what we do here on the right. And notice that even still, despite blowing it up a little bit, we can see that those edges appear to be better defined than they were in the 5D camera. Let me scoot over just a little bit so you can sort of see the difference in the color and how those edges are perhaps a little bit more jagged in appearance compared to the high resolution difference. Similarly, we can see it especially in areas where there are high amounts of changes in the pattern, high frequency pattern, as we were talking about before. We have a 5D that has a pretty strong low-pass filter to try to resolve these issues with this color filter array, and so it kind of smudges out these really fine details in our image, where we don't have to have this same filter in a foveon sensor, so we can actually resolve those fine veins in the leaf. But again, this isn't to say that the foveon wins in every case, because certainly we have more noise in the color channels than we do in the 5D, which is able to resolve that information a lot better. So like everything, we have then give and take when we are discussing digital photography. All right, let's take a quick 5-minute break. When we come back, we'll take another look at low-pass filters and continue talking about digital cameras. Welcome back, everyone. So before the break, we were talking about the difference between different couple types of sensors, in particular, those with color filter arrays, like the very popular Bayer color filter array, and a different type of sensor which uses multiple layers of photosites at individual pixels to determine color at every one, specifically like the Foveon sensor. During the break, I actually got a message from someone talking about, I think, a rumored Canon camera, which might actually be addressing this very thing that we're talking about, which is that Canon may be developing a sensor that is using this multiple layers rather than having a color filter array to try to improve the megapixel count of their sensors. It's kind of a rumor, and there's this kind of enticing video at the bottom which shows the difference between Bayer color filter arrays and Foveon type sensors, and I really want to play it, but I played a couple minutes of it during the break just to sort of see if it was going to be pretty cheesy. I think it's just going to be way too cheesy to show, so I think we'll skip that for now. But we'll probably post this link, and you can take a look at that. It's probably just really, really heavy on the marketing, and instead what we want to focus on is the technology rather than the marketing, keeping in mind that with all of these things there is a compromise like we've been talking about. So when we have then this color filter array, we have to have this filter on top of it, this low-pass filter, to try to smooth out some of the details and make sure that we don't have patterns that are more frequent than the pixels themselves. And so we can actually have a variety of impacts on the image. If we have an image that has some high-frequency pattern, like, for example, this pattern in cloth on the far left, which changes, as you can see, at a frequency of about 1 pixel. We alternate between a deep blue to a white to a deep blue to a white, particularly in the band along the center here. We can see a couple of results when we image this very thing using a sensor that has a color filter array, which is used in the center, and a sensor that uses a color filter array but resolves some of the issues by using a low-pass filter, like we can see on the right. So if we take a look a little bit more closely at the patterns themselves, we can see that here we can have the individual patterns that change, again, very quickly, so high-frequency patterns that alternate between dark and white, so on and so forth at the individual pixel location, at the individual pixel level. Then we have in the center the issues that I referred to earlier, where we could have these Moira issues or this sort of maze-like appearance, or you can even have this spectrum of rainbow because the demosaicing algorithm is unable to figure out that what it is seeing, because it doesn't have context, what it is seeing is a very high-frequency pattern and not instead actually some color that exists at that across those 4 pixels that we were talking about before. So we can have these just really distracting and frankly just very poor imaging out of this, where we have this unusual sort of maze pattern that appears and also an impact on the color itself, which is something that we may not actually want. So the fix for all of this would be to put a low-pass filter on top of it, which would then have the effect of smoothing everything out. We destroy that high-frequency pattern, but now at least, arguably, we have reproduced the color in a more accurate way, and we don't have very unusual patterns that simply just didn't exist in the original image. These considerations are actually something that we don't have to think about as consumers of digital cameras, but this is also very important for scientific imaging as well. And one of the things that, for those of you that do the graduate version of Problem Set 5, you'll be tasked with figuring out how do these imagers actually find color? How do they actually capture color? Because they may not necessarily use techniques like we have described here to try to compute color. They may use filters. They may split using a prism idea like we talked about before. But these very things are considerations that people working at sort of the edge of technology, trying to advance these technologies, have to deal with. And one of the reasons why scientists that are dealing with imagers like those on the New Horizon probe and other have to know a lot about this and also have to do a lot of processing to their images is to remove problems like this that result from the technology themselves or from the optics that they know will actually result in, or not just artifacts on their image. So one of the things that NASA does is, in fact, process these images to make sure that, especially when they release them publicly, that people don't look at them and say that, oh, look, there's this little UFO-looking thing, when it's actually some reflection of light or some other error that happened on the sensor itself. They do have to do some processing to ensure that these issues, similar to this, are in fact resolved. Okay, so we've talked then about color filter arrays, and specifically the Bayer pattern. There's other patterns available as well, but that's the most common one that we see now. The impact of that, the result, is having to have a demosaicing algorithm to reconstitute the colors between all of those pixels. And as a result of this, we have fewer effective pixels than we have actual pixels on our sensor. There's competing technologies that get around this altogether by having multiple layers of photo detectors at individual pixels, and the Bayer color filter array have an anti-alias or a low-pass filter to smooth out some of these things. Are there any questions on this before we move on to other elements of digital sensors?
You're saying with this on the end, you could use a low-pass filter, but you could also just sort of change your distance, right? Because
So to repeat the question for the camera, so I'm saying that for the picture on the right, I could have either had the low-pass filter, or I could have perhaps changed my distance so that the pattern no longer repeated exactly at 1 pixel. So if I was closer, for example, perhaps it would repeat over several pixels, which might mean that the demosaicing algorithm was actually able to resolve that. That is true, yes. But, and in fact, there are some consumer cameras that are kind of specialty cameras that manufacturers have created so that actually remove that filter. But those typically are for niche markets, things like astrophotography, for example, where you want to be sure that it really is important that you capture data at individual pixels, and you have other processing that allows you to compute that information other than using a demosaicing algorithm. The problem with doing that in a consumer camera is that by moving closer to this or moving farther away, I may have then changed some other pattern that's in my image to become the same frequency. So yes, it is possible in this case I could do that, but in the general case, like even here in this room, the stripes on my shirt could potentially become high enough resolution depending on the zoom and other factors that you're taking a picture of me, or even the pattern on the carpet, or even just the pattern on your own, the stitching of your own clothes. There's a lot of things that can actually cause this to happen. And accounting for all of those factors is difficult, and so we don't see it because instead what would happen is if we were to release a camera that did that for everyone and people started seeing weird effects like this, they would think something was wrong with their camera, as opposed to having a very subtle, and this is slightly overdone to really hammer home the idea of what this low-pass filter is doing. But having a subtle amount of blurriness over maybe 1 or 2 pixels is perhaps going to be much preferred to having certain circumstances, even if they're rare, but in this case they're not really that rare, it happens pretty frequently, of having weird patterns and issues with color and moire and some other things. But yes, to more directly answer the question, changing my distance in this case would have certainly fixed that. Yes?
For the graduate students, will they need to know the demosaicing formula?
Oh no, we don't need to know for either grads or undergrads. Don't need to know the specific demosaicing formula. It's not necessary for our purposes. Okay, so let's change gears slightly and go back to this idea of dynamic range. And we're going to use this to talk specifically about the values that come out of a digital sensor. So we have here an image, and it has a certain amount of contrast. As you can see, it has a histogram that we can see up there, which in this case is an RGB histogram. It's not a luminance histogram. What kind of a looks wrong with this scene? And it might be difficult to tell as I just showed you this image for the first time, is that perhaps the contrast in this image is just too low. Perhaps there's some elements of this picture where the whites could be whiter, the darks could be darker, and I could take this histogram, as we've talked about before, and spread it out a bit, improve the contrast, and change the apparent dynamic scene, the apparent dynamic range of that scene to match a little bit more closely the dynamic range of the camera. So improving the contrast here was sort of an overall win in this particular case, even though, frankly, I just kind of faked this low contrast image. So this is just a review of something that we've seen in the past. But there's an important element here, which is that if I were to take this same image, and if this was a JPEG image, and I were to increase the contrast even more, what you would expect to happen will happen, which is that the darker areas will become darker, the lighter areas will become lighter. But it's also important to realize that I have a fixed number of values, particularly for JPEG file types or other 8-bit file types, where the more I spread them apart, the more gaps I'm going to have between those values. So I have a histogram that looks like this, which looks relatively smooth and relatively continuous. But if I really increase the dynamic range, or if I really increase the contrast of this image, we get something that looks a little bit like this. So sure, now we obviously have adjusted the contrast way too much on this particular image, but that's okay. What we want to look at specifically is the histogram up in the upper right. Notice that it specifically has apparent gaps between values. And this results from exactly the thing that we've been talking about, where we had a fixed number of values, and they were 8 bits, and this was a histogram that shows those 256 discrete values that can be represented by that 8-bit value. And by spreading them out farther and farther and farther, we're not going to be able to create intermediate values. We're going to just have to split them apart from each other and get these apparent gaps in the histogram. Now, this doesn't, at this extreme, we don't really see the impact on the image. But if I were to keep going and just continue to increase the contrast such that those gaps then would become wider and wider and wider, what would be the impact on the image itself? So one thing is the obvious case, which is that, sure, it'll look more contrasty. Areas that are just a little bit dark will definitely become darker. Areas that look a little bit bright will become brighter. But is there another impact that this will have on the image? If I'm separating these values, I'm eventually going to separate them enough that I no longer have smooth gradients between values in this image. So I can get an effect called posterization, which is so named because of old school posters would have not necessarily smooth gradients, but would be like individual colors. And what we would see in gradients is perhaps a light shade of blue over here and a darker shade of blue over here with no smooth gradient between that lighter shade and that darker shade of blue. We'll show an example specifically of this in just a little bit, but that's an extreme example of what we are doing by separating these values, is that we will eventually start to see this issue of posterization in our image. In fact, let me make sure that I have a specific example here. Maybe what I have to do is to actually open this in Photoshop to make this a little bit more apparent. So right now what I'm doing is just loading up Photoshop off screen. It will come up in just a moment here. I'm going to load an image that has a gradient like this. And let's take a look at the histogram. We can see that we have a specific histogram here, and that's all well and good. But now let's adjust the contrast on this image. So I have here my contrast adjustment. I'm going to increase the contrast quite a lot. Notice how it has impacted the histogram here, we're starting to see gaps between those values, and that's because it's doing what we told it to. We asked it to split these values apart. It's going to have to pick regions where it's going to insert those gaps. You can also see how it's actually increased the contrast of this image as well. So let me go ahead and click OK, and let's see if we can actually do this again. Modify the contrast yet again. And obviously, this is an extreme example. But notice what's happening is that here we're still separating these values. We're still now increasing the gap between these individual gradients, between these subtle variations in color. And what we are seeing is that we no longer have smooth color gradations in this sunset, but instead what we see is a harsher transition from black to a slightly lighter blue to a slightly lighter blue to white. And this is the effect of posterization. In fact, we can go one more just to make it even more apparent of what this actually looks like by splitting these values so far apart that we no longer are able to create intermediate values. So this is maybe a bit of a word of warning, but if you are increasing the contrast by essentially 300% like I've done here, then you're probably going to get some artifacts, including posterization. But this alludes to something important, which is that we have a fixed amount of data in an 8-bit image. And when we try to manipulate that data, we're going to be manipulating it, and we might have to throw away some of that information depending on what we want our result to be. So remind yourselves what a bit and a byte are. A bit is just 0 or 1. A byte is a collection of 8 bits. And so a byte or 8 bits allows us to store 256 discrete values. This is all review, hopefully, at this point, from the value 0 all the way up to 255. So let's think about this in a slightly different way. Let's think about how we have to take a signal that's on our digital sensor, which was using that circuitry that we showed before, and it has a fancy photodetector that allows us to measure in voltage, essentially. It's an analog device. It allows us to measure in voltage what the value of the brightness or the intensity of light at a specific location is. How do we then convert that into some digital number that allows us to perform this modification? Well, there's a device in a camera called an analog to digital converter that does precisely this. That given some voltage, it will then pick an appropriate digital value for that original voltage. So let's take a look at what might happen in a very high level. We have on the far left a sensor, which is an analog device because it's going to record a voltage from some voltage, within some range of one voltage to another. And it is that voltage that represents the brightness or the intensity of light at that pixel. We're no longer worried about color or anything along those lines here. We're just looking individually at an individual pixel and trying to convert that into some digital value. So in this example, just to oversimplify things and just to make things a little bit more clear, we're going to say that when the pixel is empty, that there's no photons that have hit that pixel, the photosite registers no brightness values at all, we will say that it is empty at 0 volts. And if it's full, then we'll say that it is at 1 volt. And so in this case, we want to say that we've collected enough photons that all of a sudden this photosite has now changed its charge to be an approximate value of 0.55 volts. So it's kind of this middle gray-ish tone. But now what we need to do is to convert that into some digital value. So the analog to digital converter is, hand-waved basically here in this gray arrow. But it is essentially going to take that value and try to convert it into some 8-bit sample. So which means if we have an analog to digital converter that is 8 bits in resolution, that means that I can have a total number of values of 255 at every single pixel. And this might make sense, right? If we have cameras that are commonly outputting JPEG files, which are 8 bits, and each one of these pixels is going to be either red, green, or blue, and so it just corresponds very nicely to individual color channels of red, green, and blue, and that is what is 8 bits. And this seems to work out well, right? But let's think about what is going on behind the scenes here if we were to simplify this analog to digital converter slightly. This is an 8-bit sampler, an 8-bit analog to digital converter. It just so happens to convert it to this digital output here. That's fine. That string of 8 bits, collection of ones and zeros. But let's imagine for just a minute that I was building my first digital camera, and I'm building my first analog to digital converter, and what I really need to do is to create a simple analog to digital converter. In fact, one that is only 1 bit. What would this mean for my image if I have a 1-bit analog to digital converter? Which means that it can only register what values if it's 1 bit? On or off, 0 or 1, because it's only a single bit. So depending on the voltage, it is going to have to represent that voltage as either a 0 or a 1. But a sensor is an analog device. It can provide to us a range of voltage anywhere between this voltage of 0 and 1. It could be 0.55, it could be 0.25. It could be anything in between, all the way from 0 to 1. So this means that essentially what I'm doing is I am taking this analog device that might have a certain amount of data, and I'm shoehorning that information into however many bits I'm sampling in my analog to digital converter. So let's think about this yet another way, which is that we have a dynamic range that's capable, that our sensor is capable of, which was, as we've talked about many times now, is sort of this difference between the maximum voltage and the minimum voltage. This oversimplification of 1 volt to 0 volts doesn't really make a lot of sense because it doesn't really hint to us the possible dynamic range that's out of the sensor. But instead, we have a certain number of photons that will overfill this pixel and beyond which will be too bright for us to capture. But that is very important, this interplay between the possible dynamic range out of this sensor and the 8-bit, or rather the analog to digital the converter that allows us to sample that information. So let's think about this now, tying all of this stuff together in some way, which is that if I have an analog sensor that has some amount of values, let's say that, or let's consider this a different way. Let's say that I have this many photons in this pixel right now, and I receive a value of 0.55. What happens if I have a neighboring pixel that has an intensity of light that's 1 stop brighter? What does that mean in terms of the photons first? How many more photons is that brighter pixel receiving compared to this darker one? If it's 1 stop difference. Mm-hmm. Yeah, twice as much, right. So I have 2 pixels here. I have one that's getting a certain amount, and I have one that's 1 stop brighter. So my brighter one is getting twice as many photons. Now, it just so happens that a digital sensor records this in a very linear way, which means that if I have filled my pixel, my darker pixel, with up to some value of half, my brighter pixel that's 1 stop brighter is now going to be completely full. Because I've received twice as many photons, it's going to be 1 stop brighter. But now I've actually changed that by 1 stop, just by filling it with twice as many photons. Now this is important because when I convert this, using this analog to digital conversion, the number of bits that I have in this analog to digital converter then specifies sort of the maximum amount of dynamic range that I can have. So think for just a minute. Imagine that I have an 8-bit digital converter, which means that I can have the value, 256 values, 8 times. Right? I have 256 values. I can have it once to 128. then again to 64, then 32, and 16, and 8, and 4, and 2, 1. Now imagine that I have a sensor that has a dynamic range of 7 stops, which would be a range from 1 to 128. That means that my analog to digital converter would be able to represent values at every single stop along that dynamic range. But if I have an 8-bit analog to digital converter coupled to a sensor that is capable of 10 stops of dynamic range, then what this effectively means is that I have to throw away some of this information. I just cannot, it's just not possible for me to represent in my digital output all of the range of values that my sensor was capable of determining. And again, one way to think about this is to think about a really simple analog to digital converter, just a 1-bit analog to digital converter. I might have a sensor that is capable of a wide dynamic range, but if I have to shoehorn it into either a 0 or a 1, then I'm not really going to get a very nice looking image out of that. And so we can then, one of the ways that we would be able to perhaps improve the dynamic range out of the camera, arguably, of course, we have to have the sensor that is capable of doing this as well, but we have to have an analog to digital converter that is able to represent values everywhere in this dynamic range. So an 8-bit analog to digital converter is frankly just not going to cut it these days. We have sensors that exceed that, but even within that, we only have 256 possible values that we can use to represent the nuances in this sensor that this sensor has captured. So what we see nowadays are analog to digital converters that are much higher in sampling. They may be 12-bit or 13-bit, or we're now starting to see like 14-bit analog to digital converters, which again is a lot more values than it sounds like at first, because for every additional bit, we're doubling the number of values that we actually have. If 8 bits is 256 values, 9 bits is 512, 10 bits is 1,000, 24, 11 bits is 2048, and 12-bit would then be 4,096 possible values. Which means that if we come back to this idea of posterization, using a higher analog to digital converter might allow us then to capture those subtle gradations in, that our sensor has captured in a lot more nuance, and allow us also the opportunity to manipulate that data without worrying quite so much about posterization or other issues like that. Excuse me. So there's a couple of things here that are important to take away. One of them is that we might have this, this error of quantization where we're trying to fit some value from this analog sensor to match whatever the nearest value is in the analog to digital conversion. And if we do not have a high enough depth, a high enough bit depth in that analog to digital conversion, then we will have subtle gradations captured by our sensor that we can no longer represent with different values digitally. So we would then throw that away. And that's sort of an important thing to realize, is that along most of these steps, do we have this opportunity for us to add additional error or add an opportunity for our digital sensors to not fully represent the data as faithfully as we might hope that they're able to do. Any questions on this? Yes? That is an excellent question. So if a JPEG is only able to store 8 bits worth of information, where is that additional information? What is happening to that additional information? Let me come to that in just a second, because there's one thing that we need to talk about before we can get to answering exactly that, which is this next idea that sensors, as I mentioned before, are linear analog devices. if I double the number of photons in that sensor, I'm essentially doubling the voltage or whatever that we're using to record the value of that pixel. So what is happening behind the scenes on the sensor level is that I have some value, some number that represents some intensity of light. And if I'm going to represent one stop difference from that, then it is going to do exactly what we've been saying this whole time, which is either doubling that value or having that value. But this means that those upper values, those stops at the higher end of what our sensor is able to capture, is then made up of a lot more numbers than those lower stops of information. So imagine here that I have a 12-bit file, which means that for every red, green, and blue color channel, I have 4,096 total possible values. This is the same thing that we've been talking about like with 8 bits, but just with more values because it's a 12-bit file. This means that for the upper half of this value of this file, or not the file itself, but the value, if I have a number, if I have a value representing the intensity somewhere in this upper half, that is the brightest stop. That is somewhere within the brightest stop of information that was recorded by my sensor. So arguably then, I have a lot more values. I have a lot more subtlety and in the gradients between relative colors and relative intensities at the brightest possible reaches of my sensor. So let's come back to this idea of sensor linearity, though, where we have a literal doubling or halving based on the number of stops. So the reason that this is good is that it's actually easy to determine the brightness at an individual pixel. We can actually look at the values and compare them and realize, okay, this one is actually several stops brighter than this other value. But this is not necessarily the best thing because this doesn't make a lot of intuitive sense to us, first of all. The fact that we're saying that the brightest stops have the most number of values. And this also isn't really how we perceive the world either. You may not actually say that when you perceive the world that the brightest regions of it seem to have the most subtle gradations. And so we might say then that our eyes or our brains are not computing the world in this same linear fashion. And it is this exact thing which allows us to then take all of this information, 4,096 different possible values, and somehow shoehorn it into 256 values represented by a JPEG. Which is that we may not actually, in our view of the world, we may not actually place quite so much emphasis on these brightest stops of information or on the darkest stops of information, but perhaps whatever our eyes have been accustomed to, those middle tones that represent a well-exposed scene. Now, if you remember from the more software tools lecture from a couple of weeks ago, we were talking about the ability to apply curves to data, that we could change the output value based on the input just by changing that curve a little bit and mapping different values, dark values, make dark values darker, make bright values brighter, and that sort of thing. That same idea, a tone curve, is in fact ultimately the answer to this question of how do we then take these 4,096 values and shrink them into 256. Well, we use a tone curve in order to map how our view of the world, onto this sensor linearity. The point of the tone curve is to compress highlights and to compress shadows and to place more emphasis on those middle tones, just like we would perceive the world. So it does happen to be the case. We have been talking about this for a long time, that doubling the number of photons in a scene means that we have twice as much brightness. We have one stop brighter. But the thing that we glossed over when we were discussing that is that if we then double from 10 photons to 20 photons, that means that this brighter stop has a lot more gradation that's possible. There's a lot more subtlety in the possible number of photons, even though, yeah, it is the case that it is twice as bright than the darker version. But again, how we see is more akin to this, where we sort of remove emphasis. Our brains remove emphasis from the darkest regions and the brightest regions, and we pay attention to the subtleties and tones in those middle regions. And applying this tone curve is a very important step in the process of computing the final image from a sensor. So if you take a look at this, graph, this is a very similar graph to the tone curve graph that we were looking at in Photoshop specifically, except that the scale is a little bit different. Before, we saw a scale of 0 to 255 along the x-axis, and those were the values that were written in the file. And along the y-axis was the output. After we had performed our tone curve manipulations, that was also ranged from 0 to 255. And we applied some curve to perhaps pushing up that right side of the curve up a little bit more meant that those brightest regions became brighter, and they kind of compressed into that output. That's exactly what's happening here, is that we have in these uppermost 2,000 values, which is the brightest stop recorded by this sensor, we are compressing that by kind of pushing up that output curve like that. We're compressing it into the topmost values. And we're compressing these bottommost values into some small numbers when we actually write this to an 8-bit file. And so then this hints something about posterization, which is that if we have a file that came out of our sensor that has 4,000 values as opposed to 256 values, we have a lot more leeway here to manipulate this information, and a lot more subtlety in these gradients that would allow us to change the contrast of our image or do drastic manipulations to this file without separating those values quite as drastically as we did in 8 bits worth of information. So posterization then is arguably not as prevalent of a problem when we're operating in a higher bit depth. It's much harder to achieve posterization, which maybe is something that you're going for. That might be an artistic choice, but arguably that's not something that we generally want. So one way to combat that would be to operate at a higher bit depth, or even at the bit depth, ideally, that was output by the analog to digital converter in your camera. So let's take a look then at the difference between RAW and JPEG. Now that we can actually talk about a lot of these things in the context of digital sensors and in the context of everything that we've talked about up until this point. A RAW file might have a bit depth that is very different from JPEG. It's not necessarily specified. As we talked about, RAW files are unprocessed, and they're different from camera to camera, well, from manufacturer to manufacturer and camera model to camera model. But the bit depth might be 10, 12, or even 14 bits, which, again, is a lot more than it sounds. Like 12 bits, for example, was 4,000 values, as opposed to 8 bits, 256 values, which is an enormous change. So the tone curve in a RAW file is not yet applied, whereas some default tone curve is applied when your camera is processing that file to be a JPEG output. Sometimes you will even have simple, the ability to make simple manipulations or modifications to your camera's tone curve by changing the amount of contrast. It might say, you might have a JPEG option in your camera, and you might say, oh, I want it to be standard or vivid or extra contrasty or portrait or something like that. And that is essentially just applying different tone curves to the output from your sensor before it's written to the JPEG. The white balance is not set. This is something we'll talk a little bit more in the color lecture, I think, next week. We've talked a little bit about compression. Generally, RAW files are losslessly compressed, which means that we are able to reconstruct all of the original information, whereas JPEG throws away some information that the designers of the algorithm thought that we wouldn't really care about that much. It does a very good job at that, but it is throwing away information in a way that we cannot reconstruct all of the original values that constituted that image. Portability here, again, is just a way of measuring how easy it is to take that one file and move it from one computer to the next, make sure that it is interpretable or viewable by other computers. Generally, you have to have special software for RAW, as we talked about. You generally have to process it and do a variety of things. JPEG is a very standard file, on the other hand. And as a result of that, post-processing RAW becomes required. But you have a lot of this leeway with RAW files that you simply do not have in JPEG. So we've alluded to all of these things in the past, but hopefully now you're a little more convinced as to the reason why using RAW is so powerful. It's because you have access to all of those values that made up the original image, which in the case of even just 10 bits of an analog to digital converter is a lot more values. And 12 is even more. And I'm sure that many of your cameras are probably in the range of a 12-bit analog to digital converter mated to your sensor. But this also kind of hints to something else which we sometimes hear a little bit about in the context of digital photography, which is that we now, due to this sensor linearity, we actually have some values, some stops of information that make up the bulk of values in our file. And you might hear this term exposed to the right, where the ideal goal is to take the scene and expose it as bright as possible without overexposing any element to it. And this is actually pretty hard to do because generally the dynamic range of scenes are such that it is already pretty close to the maximum dynamic range that our sensors are capable of capturing. But if you have a studio setup or you happen to be in an area where there's just not a lot of dynamic range, then this might actually be a pretty good idea, which is to say that if I have 12 possible stops of dynamic range because I have a 12-bit analog to digital converter and it's perhaps well suited to match a 12-bit sensor as well, that if I do not expose all of the values, if I do not expose that scene such that it's relatively bright but still not overexposed, then I perhaps am losing a lot of potential gradation and subtlety in those values that we get from these upper stops. So again, because of this sensor linearity, because that topmost stop represents half of the values, because the top two stops represent 3/4 of the values in my 12-bit file from 0 to 4096, I'm throwing away the maximum capabilities of my camera by not trying to expose and put most of the values inside of those upper exposures. So essentially here you would have to then make sure that the tone curve is not applied because you would throw away all of that data and the compression of it. But if you take photos in RAW and you're in an opportunity to increase the relative exposure of your scene and not overexpose it, then you would be able to represent a lot more subtlety in those values by doing this exposing to the right, pushing these values into these upper stops and getting more information out of your camera that way. There's a huge risk here of blowing out individual color channels, of accidentally overexposing your image, and so on and so forth. But if you're able to control those well, then you're arguably able to get the highest amount of signal to the lowest amount of noise, improve that signal-to-noise ratio that is vitally important in our digital sensors to get the maximum possible quality. So this is really, if you want to get the absolute highest possible quality out of this, in practice, if you're out just taking like travel photography, doing portraits or whatever, this will probably be more hassle than it's worth, just because you will tend to accidentally overexpose things as opposed to when you have the ability to absolutely control every element of it. But here, consider the implications and consider then what this means, that if a sensor is linear, try to wrap your head around the fact that these upper few stops that our sensor is capable of capturing represent the most amount of values. That has implications for us, especially because we then have to take those values and try to fit them using a tone curve into a relatively lower amount of bits. Any questions on this? All right, a lot of stuff to digest, but hopefully this demystifies some of the things in a digital camera. We'll talk a little bit more about this, I'm sure, in sections, and if you have any questions, please do let us know. But that's it for today. I want to thank you all very much for coming. We will see you again next week.